Hello, guys. I'm sorry about yesterday. I just was feeling really, really bad, but at least now I'm feeling a little bit better. So here it is, the video that I'm going to go over lectures 5 through 9, because I know you got your exam is coming up in a week, so I know everybody's kind of stressing right now. So we'll try to get through it. Plus, I will be holding office hours on Saturday. I will be sending out a group me to see what times works for everybody, because I want to make sure that, if you have any prior commitments, it won't affect it that much, but I'll just be posting this in the group me, okay? Let's just start. So announcements. Dr. Duma did remind me that you guys do have the Piazza page where you can ask question there, and I know one of the TAs personally, and she's amazing. So that's a really great resource if you have any questions. Dr. Pooch does hold office hours, so that's also a great resource if you're having some issues with the material. And for next week, we're going to be going over the last three lectures, lectures 10, 11, and 12. Plus, I hope that we're gonna have time towards the end of the presentation, but we can have a little exam review where you guys can ask any questions you guys have, and I'll probably have some exam questions as well, just to see like how you guys are doing, or we can address any issues that you guys are having with the material. Okay. So for lecture 5, we're talking a little bit more about protein structure. Okay. So there's these crucial roles that proteins have in our body, right? They can work as antibodies, receptor channels, molecular motors, enzymes, structural elements, transporters, and transcription factors. So these are really important for you guys to know, because I remember in my exam, he asked a question about this, like straight up, like true or false, like are any of these the roles for a protein, right? So one way that I did memorize was this armrest. Obviously, receptor channels was kind of repeated, but it had to be done, right? But this is a good way to at least memorize all of these protein roles, right? Another important thing to know is that protein sequence isn't so, or protein when they're starting to bend and create their 3D structure is not sequential, right? So especially in textbook, it has some notion that as soon as proteins leave, like proteins will only start modifying themselves or bending as soon as it leaves the ribosome, right? That's not necessarily the case, right? It's going to start bending as soon as it leaves the rRNA, or the RNA is just the structural component of our ribosome, right? So it does not occur. So the bending does not occur after the primary sequence has formed or properly formed, right? As soon as it leaves the ribosome, it's starting to bend and create that 3D structure that we know of. So here's a really great video going over the primary, secondary, tertiary, and quaternary structures. I'm not going to be going over, but I would recommend at least watching this before your exam, because it does a great job of explaining all four elements or four structures of a protein, right? So an important thing to know, especially when we're talking about the primary structure of a protein, is this peptide bond, right? This peptide bond is very, very important, okay? And that's because this peptide bond is probably the only bond involved in a peptide or in a protein that doesn't really move that much, right? And that's because the CN bond right here has a 40% double bond character. And this is due to the resonance of this carbonyl oxygen right here and the nitrogen. So it has like a delocalized electron cloud covering this area right here, okay? And if we remember a little bit from organic chemistry, we know that double bond characters do not like bending, right? Because remember that a sigma bond has an overlap of the molecular orbital, but a double bond character does not have any overlap. So they're constantly in this perpendicular state, like making that attraction right here, but there's no overlap. So that means even a little bend either way can disrupt that connection, right? So that's why it doesn't like moving that much. So if we look at this diagram right here, we can look at the different bonds and their designations, right? So we have our psi, our omega, and our phi. That's crucial for you to know for your exam, okay? Because he can easily just ask, oh, like what's important about the phi bond, right? And you have to know, because he won't just go like the nitrogen carbon bond, right? So be aware that you have to know these designations, okay? So when we're looking at the omega bond, which is the most important one that we're talking about right now, it has compared to the other ones, it has less degrees of freedom, right? So degrees of freedom are just basically where it can move and where it can rotate, right? So usually it's in the 180 degrees of freedom state, okay? So it just means it's stuck in this one area of degrees of freedom, but it can be zero in the case of proline. Proline is a little bit of a weird amino acid. It's like the black sheep of the amino acid family, just because it does a lot of weird things, right? We can talk a little bit about it more later. So now we're moving into the secondary structure. And the secondary structure is defined by two very specific structures, and it's the alpha helixes and the beta sheets, okay? For the alpha helixes, or sorry, for tracking back a little bit, right? The secondary structure is defined primarily by the hydrogen bonding. So that's like the major important interaction that allows us to get our alpha helixes and our beta sheets. So our alpha helix has a 3.6 residue turn and 100 degrees of rotation, and our beta sheets can either be parallel or anti-parallel. And then for the tertiary structure, this is defined by short-range non-covalent interactions, and it also includes, for example, disulfide bonds, like the cysteines that we saw in the last lecture. It includes salt bridges, so interactions between a positive and a negative ions, right? So the tertiary structures where a lot of different interactions start coming into place alongside that hydrogen bonding. So an important component of understanding these protein structures is the Ramachandran plot. Okay, so the Ramachandran plot was divided by this really smart guy in India, and he was able to deduce what type of structures we're going to get based on the degrees of freedom of our psi and our phi bonds, right? And remember, omega isn't included here because omega doesn't turn that much, right? So for example, if we have a degrees of freedom of for psi at 120 and a phi degrees at around like negative 160, we're going to be around this area right here, right? And this corresponds to an anti-parallel beta sheet. So these were really, really important. So I'd recommend for your exam to know what this means, you know what the Ramachandran plot is trying to tell you, and at least know these three areas right here of where these types of structures are going to be located, okay? He rarely asks detailed questions about the Ramachandran plot, but I know for a fact that at least these areas right here are going to be the really important ones to know, right? And then looking back at it right here, this white area is where energetically unfavorable steric clashes are defined. So this is the areas where you're probably not going to find any amino acid with these types of rotations, right? So just know, and again, understand the structural features in this plot, okay? I don't think he's gonna ask that much detail on it, but just be able to kind of locate some, especially these three right here, on where they're kind of located in this plot, just in case, right? Again, there's a lot of ifs and like speculation on what this exam is gonna look like, but I'm kind of fair that he will at least have a conceptual question on the Ramachandran plot, but I doubt that he's gonna have a very specific question of where this structure is gonna be located, right? And I also included a little video here explaining the Ramachandran plot a little bit in more detail if you're having some issues understanding what it means. So now we're just jumping into the quaternary structure. So the quaternary structure is when multiple tertiary structures are put together. They're intrinsically asymmetrical and they can be either arranged in a rotation or translation method or structure, I mean. And an big example he gave us is tropocollagen, right? So tropocollagen is a trihelical. It has glycine proline and hydroxyproline, okay? So this has a head to tail assembly, and then hydroxyproline is going to use their hydrogen bonds to stabilize the whole structure. And we also have covalent crosslinks. That's what makes tropocollagen such a strong structure and why it's involved in the mechanical integrity of our skin, some of our tissues, for example. Be aware that tropocollagen, he does like asking some conceptual questions on what tropocollagen does. For example, like, what amino acids are involved with tropocollagen, or like, what does hydroxyproline do, which is, use its H bonds to stabilize the structure. So be aware that tropocollagen usually does come up in his exam, right? Okay. So for lecture 6, we talk a little bit more about protein folding, unfolding, and misfolding. So there's two important characteristics for a protein. A protein has specific binding and specific activity. So for specific binding, it means it only binds to a specific substrate, right? And for specific activity, it just means it's able to do only one function, right? So protein synthesis and folding occur at the same time, right? So as we looked around before, right? As soon as it's coming out of that ribosome, it's already starting to fold, right? But we do have sometimes proteins that help us fold a little bit better. These where the foldases and chaperones come in. An important paradox to talk about is the Levinthal paradox. So the Levinthal paradox came with the idea that if you have a huge primary structure, right? And if each bond had to rotate in a certain degree, and if it was sequential, it would take so long to find the proper structure, right? So what this Levinthal paradox is trying to tell us is that every bond that's able to rotate is trying to find its most stable conformation at the same time. That's why we mean by a massive parallel search, right? Because each bond is individually trying to find its lowest energy state or lowest energy conformation all at the same time, okay? So that's why protein folding occurs pretty quickly, okay? So then we come into the topic of denaturation, right? So denaturation is basically when a protein loses its 3D structure, right, to some degree. And that can happen through a bunch of cases, right? Heat is a pretty big one. That's why like high fevers are pretty dangerous, right? Because they can like affect some of our proteins. Urea is also a big one, and like detergents can also affect protein, okay? So an important experiment is this Infinson experiment. Again, I don't know. I had a question on the group me about do we have to know the people and stuff like that. I wouldn't. I don't. Again. This is like I'm 90% sure you don't need to know the names of the people, but it could help you understand because he will ask questions about like the Infinson. I can't say this name. Infinson experiment, right? So at least know the title of the experiment, or at least know what the experiment was trying to tell us for the greater scope of biochemistry. Okay. So for this Infinson experiment, this proved that the primary structure determines the 3D structure, right? So as we see right here, we'd have this native ribonuclease. Then we use a reducing agent. In this case, it actually disrupted the disulfide bonds that occurred right here. And then we heated it up, or added more urea, and that completely destroyed the 3D structure. But once we cooled it down or removed the urea, we noticed that the 3D structure slowly came back, right? So that's what we mean that the primary structure was able to determine what the 3D structure is going to look like. So what is protein folding not? So it's not all or nothing, and it's not a linear multi-process, right? So when we say it's all or nothing, it doesn't mean that as soon as it's finished, it's completely done. It's never going to change again. It can still modify itself, even though it might be in an active form, right? And when we say about a linear multi-process is what we meant by the massive parallel search, right? It's not going from each bond to each bond, slowly making sure that each bond is in its proper conformation, right? It's all occurring at the same time. So what protein folding is a massive search to find a proper structure. And this occurs simultaneously all over the protein, and it has a bunch of little misfoldings all occurring at the same time to find the native state. Okay, so this is what we look at this diagram right here, right? We want to reach this state, and we see that sometimes the protein reaches a point and it's like, ooh, this was a mistake. We can do better, and then it just keeps going forward until we find the lowest energy, right? Until there's no more rotations or there's no more foldings to occur. So there's two main ideas about protein folding. So the first model separates it in stages, right? So there's 3 stages: the nucleation, which involves our secondary structures; the structural consolidation, which is the secondary and tertiary structures; and then final rearrangements, right? So this first model it's basically going through the stages, okay? For the second model is my favorite model, is just the molten globule model, right? So this just means that the hydrophobic interactions all come together at the same time and starts collapsing the protein and reforming itself, right? Until we get that native protein structure, okay? By the way, molten globule, my favorite one because it's the funniest one, okay? It just looks like a sundae. Okay, and there's one big example that we looked at, which is the Grow S&L 2-cylinder folding machine. So the thing they had to understand for this is just understand the general steps, okay? And you can see that a folding intermediate, or a protein that's not completely folded, enters one of the active sites, the Grow L. Then we use ATP and we close this lid up, and this allows the protein folding to occur to its native state, okay? But you can also see that we do have a Grow S, which is in the bottom of our Grow L, where another protein can actually go in and use the same process, use 7-ATP to give us the correct native protein, or the slow folding intermediate, okay? So this is just a little example of how different proteins can actually help us fold even our own proteins, right? This is just understand the general idea of what it is. You don't have to be in complete detail, okay? But also just understand that we are using ATP, right? Protein folding in this manner isn't going to be natural, right? Because we need ATP to make sure that this protein, our Grow SL, is properly folding our proteins. So what happens with protein folding gone wrong? Then we have what we call a prion disease, right? And this actually causes amyloidosis, right? And that's really bad. Okay, so there's 2 ways that we can designate a protein folding. We have our PRPC, which is the good ones that have alpha helixes, and our PRPSC. which is the bad ones. And instead of alpha helices, we have beta sheets instead. Okay. So the issue with with prion disease, when protein folding goes wrong, is that the bad proteins can actually infect the good proteins and make them into bad proteins. It's like a little zombie apocalypse, right? As soon as a bad protein gets close to a good protein, it actually misfold the good protein, making it bad and spreading that disease. So that's why it's pretty dangerous, right? That's like the basis of like mad cow disease, for example, okay? And I also put a little example of this disease right here, which is based on prion disease as well. And this is a really good example. And right here, even in the picture, we can see the alpha helix, and then we have a beta helix that's changed up, right? So now we're going to protein binding interactions. So this is going to be the major part of lectures 7, 10, and 11. So this is pretty important, right? So you have to know what KD means. KD is this equation right here. Now we can see it's talking about the concentration of proteins and ligands separately, and then a protein ligand complex, okay? So when we have a high KD, that means we have more unbound ligands, and when we have a low KD, we have more bound ligands, okay? Try to understand and see where this gets like a fraction, right? So if you have a high KD, it means we have a lot of these separated. Well, if we have a low KD, we have actually a, sorry, there's a little insect right or mosquito right in front of me. And if we have a low KD, we have more bound ligands, right? So then we go into the saturation equation, okay? So luckily for you guys, because when my class we were told we had to know how to calculate this, but I've been hearing that pH doesn't necessarily need you to calculate this, but just understand what the saturation question or equation is trying to tell you, right? So we have this question right here. This is KD, right? Right? It's the same thing as KD. Sorry, not the same thing as KD. Sorry, I said that wrong. I was confusing myself. Sorry, not the same thing as KD, right? So what this equation is trying to tell us is the fraction of total sites that are occupied by a ligand, right? If we're looking at the entirety of one protein or one enzyme, this is trying to ask like what is the percentage of proteins that have their active sites filled up, okay? So if we're looking at this question right here, we see that once we get a ratio, this is going to be the percentage, right? Okay. So it's basically trying to tell you that if we have a 0.5, if we have half of our normal KD, okay, this is going to mean that 33% of our proteins are filled up, okay? If we have exactly our KD, it means we have half. And this comes into the next explanation of what KD is, okay? KD is also indicating the ratio or the number of ligands needed to fill half of the active sites in a protein population, okay? So if we see here that we have one KD exactly as our ligand, right? As our ligand concentration, it means half of our active sites are completely filled up, okay? And it kind of makes sense, right? But again, just going back, right? KD is talking about our bound and unbound ligands, and another explanation of our KD is meaning that half of our active sites are filled up. So if we have exactly 1 KD of a concentration of our ligands, it means half of our active sites are going to be filled up. And that's going to come in. We're going to talk a little bit more in our lectures 10 and 11 about this concept, okay? So now we're going to talk about the big thing about lecture 7, which is our hemoglobin and myoglobin. Forgot the word I was going to say. Hemoglobin and myoglobin concepts, right? So hemoglobin and myoglobin are both 8 helix polypeptides. And why do we need to know hemoglobin and myoglobin, right? So hemoglobin is really important for in our blood, right? In our red blood cells, they bring in the oxygens through their heme groups, right? And our myoglobin is actually really important in our muscles because they are like a little extra reservoir of oxygen if needed. So they actually only share, even though they kind of look the same and have the same function, they actually only share 27 identical residues, but they do have their similar shape. And this happens again because protein-protein interactions are occurring at the same time, right? And protein-protein interaction doesn't necessarily mean we have the same amino acids in the same sequence, but it just means they're going to have similar properties, right? Because we know we have our acidic side chain amino acids, our basics, and they're going to function in a similar fashion, which means that we can have similar structures without having identical residues. So here is a saturation curve of myoglobin and hemoglobin. So this here I want to talk about right in the beginning, and this is explaining how oxygen, sorry, this is explaining how our hemoglobins work, right? So when we have in the lungs where we have a high concentration of high partial pressure of oxygen, our hemoglobins are going to be almost totally filled up. But when we're in a peripheral tissue where there's a low partial pressure of oxygen, our hemoglobins are not going to be filled up. And that's good, right? Because we want the hemoglobins to be filled up in the lungs, and then they bring it to our peripheral tissue where they can start disposing or leaving behind oxygen molecules for the rest of our tissues. So when we look at hemoglobin and myoglobin, so this is hemoglobin right here, the image kind of cut it off, but we see that myoglobin has this hyperbolic curve, and while hemoglobin has this sigmoid curve, okay? So the important thing to know about this is that since myoglobin only has one active site or one binding site for oxygen, while hemoglobin has four, we're gonna see that when there's a four binding site, or when there's a cooperativity, I mean, between the interactions in a protein, we're gonna have a sigmoid shape right here. So let's go back and understand what cooperativity means. So cooperativity means that there's a certain cooperation that if, especially if there's a protein that has multiple binding sites or active sites, it just means that if one of those active sites or binding sites are filled up, it's going to make it easier for the next one to be filled up, and etc. Right? So this is what cooperativity means, and hemoglobin expresses that. So there's two major models to explain the cooperativity of oxygen. There's the concerted and the sequential. So I think if you guys watch the lecture, you know which one Dr. Puich likes the most, which is concerted, right? Because I don't know, he hates sequential so much. But the concerted model, it deals in a certain way with equilibrium, right? And I like to call the concerted model the sharing model, okay? So the concerted model means that a hemoglobin can only exist either in the tense state, where it can't accept any oxygen, or the relaxed state, the R state, where when it can. There's no hybrid states, okay? And once it binds to O2, the R states start becoming more prevalent in a population of hemoglobin, okay? So this is an image right here that explains it to you, right? So as soon as more oxygen starts, as soon as the hemoglobin is in an area of high oxygen concentration, it's going to be favoring the R state, right? And once it's in the peripheral tissue where there's not a huge partial pressure of oxygen, it's going to be in the T state. So it starts dissociating oxygen, right? Um, but the important thing of the concerted model is that concerted model is actually shown to occur in the carbon monoxide example, right? So as I said before, the concerted model is like a sharing model, right? So it tries to make sure that all the other hemoglobins have the way that I like to think about this, and this is it's not like real life, but it's kind of a good to get the concept in your head, right? Think that we have like 10 hemoglobins, right? Filled up, right? And we're in an oxygen rich state, okay? So if we're in a oxygen-rich state and we're in the conservative model, each hemoglobin is going to get at least one oxygen molecule before they get a second one. Okay, so they share the oxygen partial pressure. Okay, so they go in sequence, right? As soon as one gets one, everybody gets one. As soon as they reach the second stage, all of them get a second oxygen, right? So that's like that concept, right? It's like the sharing model. Obviously, in real life, it's not going to work that easily, but it's a good way to get in your head the difference between concerted and sequential. Okay, so it shares, right? It makes sure that no hemoglobin is left behind. And when we look at carbon monoxide, this is explained by this model, right? Because carbon monoxide, if we remember, carbon monoxide binds really tightly. It has a really high affinity, or hemoglobin, I mean, has a really high affinity to carbon monoxide. Okay, more than oxygen. So it's gonna really want to get that carbon monoxide. The issue is that when carbon monoxide is bound to the hemoglobin, and if another oxygen molecule goes in, it's not gonna allow the hemoglobin to dissociate oxygen in the peripheral tissue, right? Which is a huge issue. Okay, so if we're following that sharing model concept, right? As soon as the carbon monoxide is bound to all those 10 hemoglobins, or those 10 red blood cells, right? And then the oxygen start coming in, right? We're gonna lose all of those 10 hemoglobins, right? Because the one carbon monoxide is bound to it. So that's a huge issue. Okay. And when we have these carbon monoxides bound to it, we're gonna actually have this hyper hyperbolic curve, hyperbolic curve, right? And we're going to see that we're not going to be able to dissociate as much oxygen as anymore in the peripheral tissue as we did before, right? And that's the huge issue. The sequential model is the more greedy model, okay? In the sequential model, we're going to be looking at individual hemoglobins, right? So in the sequential model, as soon as one oxygen is bound to it, we're going to be able to make the other subunit relax, and then the next subunit, as soon as one is bound to it, okay?
So that's why we have these huge drops in delta G energy. So it makes it even more favorable. As soon as one, it makes it completely favorable. As soon as there's another one, it makes it even more favorable, right? So when I say this is a greedy model, and that is because, um, for example, as we talked about, carbon monoxide loves our hemoglobin more than oxygen, right? So the greedy model is going to actually try to get all those hemoglobins just, or sorry, the hemoglobin is going to try to get all those carbon monoxides to itself first. So instead of having these versions where we're going to have one carbon monoxide and three oxygen molecules, we're going to see red blood cells that are going to have four carbon monoxides all bound to it. Okay. And this means this is not explained at carbon monoxide mechanism, because if we have the hemoglobins like trying to bind as much as possible to um, to carbon monoxide, right? Because they're greedy, they want to get it all for themselves. It means that only a fraction of those red blood cells are going to be out of commission, right? So, for example, I think the example Dr. Peach gave is like 25% of our red blood cells are going to be out of commission, but we still have 75% that can still do their job. In a conservative model, we would have an issue where like almost 100% of our red blood cells are going to be affected by it, which is why we die from carbon monoxide poisoning. In this example, it just means that only a fraction is going to be damaged, but the other ones are going to be unaffected by it. Okay. So that's like the big difference, right? So that's why I like to think of the conservative model as the sharing model and the sequential as the greedy model. Okay. So this is just a big example of both. And a very big difference between sequential and concerted model is that the concerted model doesn't allow hybrid forms, but sequential does, right? So concerted is like it's either in the tense state or the relaxed state. For the sequential model, it can have like one subunit in the relaxed state and the other one in the T state, for example, right? So that's a huge difference as well. And I know it's a little bit confusing. So AK Lectures also gave a really good video on the hemoglobin, right? I give it a watch if you're a little bit more confused. And just a little reference, AK lectures are amazing for biochemistry. Okay, so if you have any questions, like they're also amazing for all the concepts of biochemistry. Okay. To end lecture 7, we also have the Bohr effect and the 2,3 BPG. Okay, so these are the effects that can actually move our oxygen dissociation curve to the right. Okay, so the Bohr effect occurs when there's a high metabolic state that lowers the pH. Okay, remember lowering the pH is just an indication there's a large amount of physical um, activity going on because we're forming lactic acid, right? So this actually stabilizes the T state, allowing the O2 to be released a lot easier. Okay, so for example, if we're moving the oxygen hemoglobin saturation curve to the right, it just means that oxygen level or oxygen is being dissociated at a higher partial pressure than normal, which means more peripheral tissue is getting that oxygen. Okay. The other cases are 2,3 biphosphoglycerate. Okay, so this also stabilizes the T state, favoring O2 dissociation. And we're going to talk a little bit more about the biphosphoglycerate in a further lecture, but this is actually really, really important, right, for glycolysis. So now going on to lectures 8 and 9. So this is where we're talking about how enzymes work, right? So there's 6 enzyme classes, 7 technically, right? We have our ligase, isomerase, lyase, hydrolase, oxyreductase, and transferase, and ergase. Okay, so this is a little mnemonics to memorize, little hot. Okay, so what enzymes do is they actually diminish this activation energy right here. You see the difference, right? Because think of this like a little hill, right? It's gonna take a lot of energy to go through this reaction without an enzyme. Okay, so what this barrier height is reflecting is the issues that involve trying to align the molecular orbitals together, the separation of electronic charges, trying to rearrange our bonds, and other transformations like protonation and deprotonation. And enzymes help with all four of these class or these issues that um, a reaction has without an enzyme. So another more concepts to know, more Ks, right? Because there's a lot of K constants. So KQ is just our equilibrium constant, and this is relative concentration of products and substrates at equilibrium. So products over substrates. And then our little q is just the rate constant. So this just measures the speed of the reaction, okay? So an important equation to know is the Arrhenius rate theory, okay? So this is just explaining the rate constant through this equation, okay? So we have A, which means the number of molecular collisions occurring per second with the proper orientations. And then we have E negative activation energy over RT. Okay, so the important thing to know about this equation is understand what it's trying to tell you, right? So if we do have an increase in t, we're actually going to have an increase in this whole constant right here, leading to an increase in the rate constant. And that's a really big deal, okay? And the same thing is going to deal here, right? If we have a lower activation energy, this whole equation is going to increase as well, right? And this is just a math concept, but it also makes sense theoretically, right? We know that increase in the temperature is going to increase the kinetic energy of the molecules around, allowing for more collisions, which would undeterminedly lead to more reactions, right? And we also know that if we have a lower activation energy, we're also going to have a higher rate of reaction because there's not going to be that physical barrier preventing it from occurring. And an important thing to know is that enzymatic reactions are always going to try to find the the path. Oh my God, I'm sorry, I'm speaking horrible. The path of least energy, right, or the least resistance. So we have this little example of like a little hill, and we're going to see that it never goes through the peaks. It's always going to go through the little depressions, right? Because it's going to try to find the one that's not going to waste as much energy or as much time as it needs. It's always going to find the easy way through the situation. So we also have two very important concepts on the enzymes. We have our lock and key and the induced fit or the dynamic model. So why is it not a lock and key? And if we look at the diagram right here, if it was a lock and key, we'd have such a huge drop in negative free energy that there's no way that the reaction is going to go up again this long, because this now is representing almost an activation energy right here. It's going to be huge. Okay, so that's why we don't see a lock and key model, because we would have such a huge drop in this free energy that it would be stuck here. It wouldn't move forward because then we'd have this huge activation energy hill. The dynamic model and the induced fib model, we're actually going to see this right here, right? It might have a little drop, but we're actually changing the enzyme as the substrate is coming in, which is going to either increase or decrease, and it's not going to have this huge drop right here. And we're going to have a huge drop in your activation energy as well. So again, AK lectures are also amazing to explain this here. Now we're going to come into the one reaction that you're probably going to have to know for this exam. This is the chymotrypsin reaction. So there's two phases: the formation of the acyl enzyme intermediate and the deacetylation phase. Okay. So what is the catalytic triad? Right, triad. It's these three amino acids right here: aspartate, histidine, and serine. And then we have the oxyanion hole, which is just an area that can actually stabilize the transition state of this reaction. Okay. So what you need to know for this enzyme is you don't have to memorize the structures, but necessarily you'll have to memorize the amino acids regardless, right? So you kind of know most of it, but you should know which amino acids are involved, okay? So this is a great video explaining the chymotrypsin in motion. And luckily, the other SI that's working with this class right here, Priyanka, she has a great slides going over step by step of the chymotrypsin reaction if you're having issues with it. So I'm just going to leave it right here. I'm probably not going to go over it because it's mostly stuff that's from the lecture slides. So it's just repeating it, but with better images, right? Because Dr. Pearce sometimes is a little complicated with his slides. But I'll keep it right here for you guys to look at it. So this was the end of the lecture. Again, I apologize for feeling kind of sick. Yesterday, I was feeling really bad, but I hope it really didn't affect you guys that much. Again, I will be posting a GroupMe poll later today. Well, today is relative, but you'll see it in the GroupMe, and we can figure out the proper time for our Saturday office hours. Okay. Thank you again so much. Okay, and I hope you guys are having an amazing week and getting ready to study for this exam. Okay.